In this session, we shall discuss about matrices, row operations or transformations of a matrix, rank definition with respect to minor, and properties of rank of a matrix. So first let us discuss the importance of a matrix, or what's the importance of linear algebra. Matrices help us to express large amounts of data in an organized form. Matrices are single objects and perform calculations with them directly. It is convenient to express scientific and mathematical ideas. It is also useful to solve a system of linear equations. Coming to the definition of a matrix is a rectangular array of numbers or functions. A matrix can either be a square matrix or a rectangular matrix, where square matrix is a matrix which has equal number of rows and columns. A rectangular matrix is a matrix where the number of rows is not equal to the number of columns. So here are a few examples of a matrix. So you have the examples of both the rectangular matrix as well as the square matrix. How do we denote a matrix? A matrix usually is denoted by capital letters A, B, C, so on, and Aij represents the position or location of a particular element of a matrix. In general, A21 represents the element in the second row and the first column. If I have a M cross N matrix, M represents the number of rows and N represents the number of columns of a matrix. So if M is equal to N, this represents a square matrix where the number of rows is equal to the number of columns. If M is not equal to N, this represents a rectangular matrix where the number of rows is not equal to the number of columns. What is a vector? A vector is a matrix with only one row or one column. A matrix with only one row is called a row vector, and a matrix with only one column is called as a column vector. In general, a row vector is of the form A is equal to A1, A2, A3, so on, An, which means a row vector has only one row, any number of columns. For example, the matrix A is equal to 9 minus 2, 5 is an example of a row vector since it has only one row. Similarly, a column vector is of the form B is equal to B1, B2, so on, Bm. So a column vector has only one column but any number of rows. An example of a column vector is B is equal to 10 minus 6, 0. Coming to elementary row operations or row transformations of a matrix, there are three types of row operations or row transformations of a matrix. The first transformation is multiplying a row by a non-zero constant, which we call it as scaling. So I have considered a random matrix with elements 1, 2, 3, minus 2, 4, 6, 0, minus 5, 1. So I am applying the row transformation R2 multiplied by the constant 2. So when I multiply the second row elements with the constant 2, I get the resultant matrix as 1, 2, 3, minus 4, 8, 12, which is obtained by multiplying the second row of the original matrix by the constant 2. The first row and the third row are retained as it is. The second transformation is interchanging any two rows. So I can interchange any two rows. I can either interchange R1 with R2 or R2 with R3 or R3 with R1. So I have considered the same original matrix and I am interchanging the second row and the third row. So when I interchange the second row and the third row, the first row is retained as it is 1, 2, 3. So the third row now becomes the second row and the second row now becomes the third. So this is called as interchanging of any two rows. The third transformation is adding a multiple of one row to another row. So we consider the same original matrix. The transformation I have considered is R1 plus 2R2. So what does this represent? So I am adding the first row elements with twice the multiple of the second row elements. So I will get the resultant matrix as minus 3, 10, 15, minus 2, 4, 6, 0, 5, 1. Since I am applying the transformation on the first row, only the first row elements are changed. The remaining two rows remains unchanged. So how did we get minus 3, 10, 15? So R1 plus 2 R2. So I am adding the first row elements with twice the second row element. So I get 1 minus 4 is equal to minus 3, which is the first element here. So how did we get 10? So similarly 2 plus 2 into 4 we get 10. How did we get 15? 3 plus 2 into 6 we get 15. So these are the three types of elementary row operations or row transformations of a matrix. Coming to the definition of rank of a matrix. What do you mean by rank of a matrix? So if I consider a M cross N matrix, rank of a matrix is not restricted to only square matrices. Rank of a matrix is also applicable to a rectangular matrix. So I'll consider a M cross N matrix. So the matrix A is said to have rank R if there exists at least one minor of order R of the matrix A which does not vanish, and all minors of order R plus 1 must vanish. What do we mean by minor? Minor is the determinant of the matrix obtained by deleting the row and column in which the particular element lies. Coming to the denotion of a rank of a matrix, it is either denoted as row of A or rank of A. So let us discuss how to determine the rank of a matrix by the minor method. Determining the rank of the matrix by the minor method is not a preferable method, as it's quite a tedious job to obtain the minors when the order of the matrix increases. So it's not an easy job to determine the rank of a matrix by minor method. So I have considered a 3 cross 3 matrix. So since it's a 3 cross 3 matrix, I can evaluate the determinant of the matrix, right? So the determinant of this matrix we get as 0, which means it's a minor of order 3 which vanishes, right? Minor of order 3 is nothing but the determinant of 3 cross 3 matrix which vanishes. Vanishes in the sense it becomes 0. So when the minor of order 3 vanishes, we need to consider a minor of order 2. There are several possibilities of extracting 2 cross 2 minors from this particular matrix. I can either consider 1, 2, 3, 4 or 2, 3, 2, 3, 4, 5 or 3, 4, 4, 5 or 4, 5, 5, 6 or 1, 2, 4, 5 or 2, 3, 5, 6. So several minors of order 2 can be extracted from this particular matrix. So I must extract any one minor of order 2 which becomes non-zero. So I need to go on extracting all minors of order 2 until I get a non-zero minor. If at first instance I get the minor of order 2 as 0, I should go on extracting all the possible minors of order 2 until I get a non-zero minor. So in my first instance itself, I consider 1, 2, 3, 4. So we have got the minor value as minus 2. So which is non-zero. So since it is non-zero, the rank of this particular matrix is 2. This is a tedious job when I get a matrix of order 5 cross 5 or 4 cross 4. So when the order of the matrix increases, this particular method is not a preferable method. Coming to properties of rank of a matrix. Rank of a null matrix. So null matrix is a zero matrix. Zero matrix is a matrix whose all elements are zeros. So it's always 0. So rank of a null matrix is always 0. Because the minor, whatever minor we extract will vanish, because the determinant of a zero matrix is always 0. The second property, rank of a matrix is greater than or equal to 1 if it is a non-zero matrix. So rank of a matrix is always greater than or equal to 1 if it is a non-zero matrix. Row of in, which means rank of in represents the identity matrix of order n. Identity matrix of order n. Identity matrix is a square matrix whose principal diagonal elements are equal to 1. For example, identity matrix of order 2 is given by 1, 0, 0, 1. So if I consider the determinant of this particular matrix, I'll get it as 1. So the minor of order 2 does not vanish, which means the rank of the identity matrix of order 2 is 2. So in general, a rank of identity matrix of order n is n itself, where n is the order of the matrix. Coming to the fourth property, if A is a matrix of order m cross n, it can be either a rectangular matrix or a square matrix in general. So if m is equal to n, it gives you a square matrix. If m is not equal to n, it gives you a rectangular matrix. So if A is a matrix of order m cross n, then the rank of A is always less than or equal to minimum of m comma n. So why is it less than or equal to minimum of m comma n? So if I consider a rectangular matrix, say 1, 2, 3, 2, 4, 5. So with random element, this is a matrix of order 2 cross 3. So why is the rank of the matrix less than or equal to minimum of m comma n? The maximum possible order which I can extract, maximum possible order of the determinant which I can extract from this particular matrix is only 2 cross 2, because I cannot extract a 3 cross 3 determinant from this particular matrix since it contains only 2 rows. So the maximum possible order of the determinant of the matrix is only 2 cross 2. So since it is a 2 cross 2 minor which I can extract from this particular matrix, it should be minimum and not maximum. So the rank of the matrix of order m by n or m cross n is always less than or equal to minimum of m comma n. So for this particular example, it is less than or equal to minimum of 2 comma 3, so less than or equal to 2. Coming to the fifth property, if A is a matrix of order n, so it's understood since A is a matrix of order n, it should be a square matrix, and A is non-singular. Non-singular matrix is a matrix whose determinant is non-zero. So if the determinant of the matrix is not equal to 0, then the rank is equal to the order of the matrix. So if I consider a 3 cross 3 matrix and I get the determinant as non-zero, which means a 3 cross 3 minor does not vanish, hence the determinant, hence the rank of the matrix is the order itself. So the best example is, we can go back to the identity matrix for this. So when I consider a 3 cross 3 identity matrix and evaluate its determinant, this will be non-zero. So whenever it's a 3 cross 3 minor, so this is a 3 cross 3 minor which does not vanish, so the rank of this particular identity matrix will be 3. If A is a matrix of order n and A is singular, that is determinant of A is equal to 0. So singular matrix is a matrix whose determinant is equal to 0. Then the rank of the matrix is less than the order of the matrix. So if I consider a 2 cross 2 matrix, say 1, 2, 2, 4, and if I evaluate the determinant of this matrix, 1, 2, 1, 2, 2, 4, we get the determinant of this matrix as 0, 4 minus 4, which is 0. So since the determinant of the matrix is 0, that is, it's a singular matrix, the rank cannot be equal to 2, right? The rank cannot be equal to 2 because the minor of order 2 has vanished. So we need to write the rank of the matrix. So this means the rank of the matrix is less than 2. So the only possibility for that particular matrix which should have a rank is, it is 1, because it's a non-zero matrix. Rank can never be equal to 0, and also rank of the matrix cannot be negative. So rank of that particular matrix 1, 2, 2, 4 is 1. So the rank of this particular matrix is 1. So these are the properties of the rank of a matrix. We shall discuss about obtaining the rank of the matrix using the echelon form in the next session. Thank you.